I'm no electrical engineer, so forgive me if I don't see how the term resistive tells me the power factor equals 1. I found the following in the reference handbook. If a power factor or phase is not given in the problem, are we to assume the power factor is 1? Probably yes. In an ideal world, everything would be easy if the power factor was always 1. And since everybody on this call is a mechanical engineer, we probably don't want to get too deep in the weeds. But having dealt with this in the workplace for a while, I probably got a little bit too far into the weeds, and that's why it found its way into this problem. I probably encountered a similar problem that threw me off because it included power factor, and I was like, oh, we've got to get that in there. So let's take a couple minutes just to kind of step back and talk about power factor. And some of the stuff, some of you guys may know, some of it might be totally, out of left field. I think I cover this somewhere in the program. It might not be in this particular solution video. It might be in the fundamentals or something like that. But it's been a while since we covered this on office hours, so let's take another shot here. So yes, this term resistive implies that the power factor equals 1. There basically are two fundamental electrical equations that we have to care about. No matter what kind of engineer you are, you have to care about these. The first is Ohm's law, which is this idea that V equals IR, current times resistance. The other is P equals IV, so power equals current times voltage. But that's not the whole story, because the power calculated that way is actually the apparent power, which is the kVA, or just VA if it's not times 1,000. That's the apparent power. And if the power factor equals 1, then the real power, watts or kilowatts, is the same as the apparent power, and we never get into the weeds. And that's the world most of us live in most of the time. But every once in a while, there's a power factor. And the power factor, well, there's always a power factor, right? Just sometimes it's unity, it's 1. But in general, the power factor is the real power divided by the apparent power, which is the kW over the kVA. And that equals cosine theta, where theta is the phase angle between the current and the voltage. So why does this happen? Now I'm going to draw a really bad drawing, so please forgive me in advance if this is terrible. So this is meant to be the voltage, and this is a sinusoidal function like this. And in a perfect world, the current waveform would have exactly the same kind of shape, which is to say its peaks would correspond with the peaks of the voltage. So if I were to draw some vertical lines here, this would be a perfectly vertical line. This would be a perfectly vertical line. So we say that the voltage and the current are in phase, which means that the power factor is 1. And that happens in a purely resistive load. So that's where that vocabulary comes from. Something like a toaster or an electric heater. It's always going to be perfectly in phase. But when we have other kinds of devices, like things that have capacitors, like computers sometimes would fit into this category, we can have a leading power factor. And when we have things that have inductors, like motors would be an example of this, electric motors, then we can have a lagging power factor. So what does that mean? A lagging power factor means that the current is after the voltage. So this whole waveform for the current shifts slightly to the right. And the opposite, leading power factor, means the whole current waveform shifts slightly to the left. And the degree to which it shifts is the phase shift. That's the angle theta. So the way that we communicate this is using the power factor triangle. And there's some version of this in the reference handbook, but I remember looking at it, finding it a little unsatisfying. So I'm going to just redraw it from memory here. And if this doesn't reconcile perfectly with what's in the reference handbook, then I don't know. I'll apologize for NCs, I guess. But anyway, the apparent power, the kVA, is the hypotenuse of this triangle. That's what we get when we take the product of the current and the voltage. And by the way, all of this assumes that we're talking about a single phase power circuit. If we're talking about three phase, the formula changes. Not the concept of the power factor, that stays the same, but there's going to be some threes or root threes in there. And you should probably refer to the table for calculating the power of an electric motor in the reference handbook for that. But we'll just stick with single phase. I want to get the concepts across here. So the kVA is the apparent power. The kW is the real power. And the reactive power, kVARs, is what goes across from the angle. This is the reactive power. So when we say we have a fully resistive load, that means there's no reactive component. There's no capacitance and there's no inductors in there, which means the kVARs are zero, which means that theta is zero. So the hypotenuse gets lower and lower until it collapses with the horizontal axis, and the kVA equals the kW. They're the same thing. The power factor is unity. That's our simplified ideal case. But again, when we have reactive loads, and again, this is a function of the load. So this is the toaster is resistive, the computer is leading power factor, the electric motor is a lagging power factor. So how do we remember which is leading, which is lagging? There's a little mnemonic that you can remember. It's silly, but it's effective. It's called Eli the Iceman. Anybody heard of this?
I haven't.
No, nobody's heard of Eli the Iceman. So E is meant to represent electromotive force or electrical potential, which is code for voltage. Usually we use the variable V for voltage, but in some spheres of electrical engineering, they use E for voltage. So you have to kind of remember that for this to work. I is current, just like we're used to. And C is for capacitive, and L, you probably know if you've touched on a little bit of electrical engineering, then you know that, or you'll remember that. C is for capacitance, and L is for an inductor. It's the inductance in an electrical circuit. So Eli, you have voltage comes before the current. So voltage leads current in an inductive circuit. And ice, you have the current leads the voltage in a capacitive circuit. So if the current leads the voltage, that's a leading power factor in a capacitive circuit. Great if I could spell. And if the voltage leads the current, that's a lagging power factor. So the current, if the voltage leads the current, then the current lags the voltage. So maybe that'll help remember. And then in terms of the triangle, the power factor is always a positive number between 0 and 1. And it's always the ratio of the real power to the apparent power. So how come that number isn't different if you have a leading power factor versus a lagging power factor? Well, what happens is the power factor triangle gets mirrored about the horizontal axis. So I'll just kind of draw that as a dotted line. And theta then becomes a negative angle below. But the cosine is the adjacent over the hypotenuse, and the adjacent is always the real power, and the hypotenuse is always the apparent power. So that's just mirroring down across. But they're both positive quantities, and in both the first and the fourth quadrant, if you remember your trigonometry, the cosine has a positive value. So either way, this ratio is going to be, 0.9 or 0.85 or 0.95, whether it's leading or lagging. So we actually have to specify that it's 0.95 leading or 0.95 lagging. Now we know if the load is something like an electric motor, it's going to be 0.95 lagging. In this case, the problem statement told us that it was resistive. So we were able to to know that there was no reactive power, no kVARs, and the power factor was 1. Anyway, that's probably more than you care to know. And again, the answer to your kind of question here of like, can we assume the power factor is 1? Probably yes, unless it seems like that's what the problem is getting at, and they're like testing you on your knowledge of power factor. Then I would want to be aware of this stuff so you could try to apply it. But yeah, we shouldn't have to go too deep. If my colleague was I have a friend that's basically like the version of me for electrical, and I'm pretty sure if he heard me talking about this stuff, he'd be jumping in there. So don't take anything I said as gospel. I'm definitely not an expert on this stuff, but this is what I've had to know to get just to kind of get my way around power systems in work previously. So hopefully it helps some of you guys.